In this lecture, I'm going to show you a method that we have developed to deal with open systems and be able then to estimate parameters in open systems. And we are going to apply this method to two problems, basically. One is the estimation of a weak force acting on a damped harmonic oscillator. That's a problem which is interesting by itself, but also it serves a pedagogical purpose because it's a problem for which our method yields the exact analytical solution of the problem. And it's very useful to look at it to see how it works within the framework of a specific problem. And then we are going to apply these methods to the estimation of phase in a lossy interferometer. And I'm going to show you that we get with this method also analytical bounds. Not only losses of photons, but also phase diffusion. We can apply to phase diffusion as well. So we'll have therefore three examples of applications of this method. And the same method will be useful also for the fourth lecture when we are going to discuss the time-energy uncertainty relation from the point of view of quantum metrology. And then we are going to see that this method allows us to generalize this energy-time uncertainty relation to open systems, for which, of course, the energy cannot be well defined. So we are going to have to replace the energy by something else. And maybe from the sequence of the course, you may well imagine that the something else will be the quantum Fisher information. Okay? So now, so let me start by reminding you of things that we have seen in the last lectures. In the first lecture, we defined for a given measurement corresponding to some collection of operators, which in general are positive operator valued measures. We defined the Fisher information given by that. These operators are generalizations of the von Neumann projection operators. The Fisher information is defined by this expression, where this P of psi x is the probability density for finding some experimental result psi if the value of the parameter is x. It's a conditional probability. This can also be written like that. And we have also defined the quantum Fisher information, which is obtained by maximizing this expression here over all possible quantum measurements. So the quantum Fisher information is defined by this expression here. So this is the most we can get, and therefore the lower bound for the precision in the measurement of the parameter x is given by this expression. That's a quantum Kramer-Rao bound, where n here is the number of repetitions of the experiment. So we have also shown that the quantum Fisher information for pure states has a simple analytical expression. If you have a state that evolves like that with some unitary operator that is parameter dependent, that's the parameter we want to estimate, then the quantum Fisher information is given by this expression. That's the variance in the initial state of this operator. And this operator is defined by this expression, which really means that H is the generator of the unitary transformation. Okay? So if you have pure states in a closed system, then the quantum Fisher information can actually be calculated. So we can actually do this maximization. And we have shown you, I have shown you in the second lecture how to do it and how to derive this expression here. So that's what we have seen up to now. Now let's turn to parameter estimation with the coherence now. Now what's the problem? You see, I have shown you in the second lecture that if you use this Nun state in some interferometer, then it leads to the Heisenberg limit in the estimation of the phase. So that's a good state if you have a closed system. However, if you have photon losses, for instance, you can lose a photon in this branch or this branch here, and the loss of a single photon transforms the superposition into this one or this one, depending on which branch had this photon loss. And in fact, what we have here is a transformation of this superposition here into a statistical mixture of these two states. And if you have that, that means that we have lost completely the information about the phase. Okay? So you see that this state is okay for closed systems, but it is very bad for open systems. The loss of a single photon is enough to destroy the Fisher information. Now, for a small number of photons, we can actually calculate states that are more robust to that, and that may lead us to go beyond the shot noise limit. An experiment on that was done by Walmsley and collaborators, and I'm going to describe this experiment to you just to give you an idea of what is in the play here. Now, so this is the experiment they did. You have here an interferometer, and you want to measure some phase, estimate some phase. They introduced losses here with a beam splitter. So that's an artificial way of generating some loss and a controllable way too of generating a loss. So here this beam splitter reflects part of the photons, and it's equivalent to a lossy mechanism. The initial state they prepared was this one. And you see that this is a noon state plus this component here. And this component is very important because now if you lose a single photon, this full state here, after losing the photon, remains untangled, which means that it's still sensitive to phase. So that's the trick. You must add a component like that if you have available at most 2 photons to realize your experiment. So they have a state like that. Losses, as I mentioned, are simulated by a beam splitter in the upper arm. And these states here are prepared by 2 beam splitters that are shown here with transmissivities T1 and T2. Now, you see the first beam splitter prepares this state here. You see that's the transmissivity. It's simple to show that that's the state that goes out. You see that if T1 is equal to 1/2, that means that you have a balanced beam splitter. Then this term vanishes and you just get a noon state. And that's the so-called Hongwu-Mendel interferometer. Now that's an unbalanced interferometer on purpose so that we get this 1-1 component. And then there is this second interferometer that allows to change the relative weight in this state. Okay, so that's the idea. Now, suppose then you have this state here. And then if you have either 0 losses or 1 photon loss, we get these 2 conditional states. So it's 0 losses. That means that all photons are transmitted, and this is transmissivity. So it's simple also to see that the states should become like this one. You see this one is not multiplied by any power of eta because there are no photons in the upper arm where the dissipation is. This one has 1 photon in the upper arm, so you have here the square root of eta. And this has 2 photons in the upper arm, so you have eta, just the square root squared. Okay? So that's the conditional state if you don't lose any photon. And by the same kind of argument, you can write down this state here if you have the loss of a single photon. So you get these 2 states. They have different total photon numbers. This is the total photon number here is 2. The total photon number here is 1. So one can show then that in this case, the maximization of this Fisher information here, which is the weighted average of the Fisher informations corresponding to this state and this one, will yield the optimal values of x0, x1, and x2. And that's what they have done. That's numerically done. And that's done for each value of eta. Of course, if you lose 2 photons, then the Fisher information is 0 because you don't get any information on the phase. Okay? So that's the procedure. They can actually detect the photon that is reflected. And that is done because for getting the Fisher information of this state here, which has lost 1 photon, you must adjust the phase here for the detection. There is some optimal detection phase, and they have to know if you have lost 1 photon or not. So what does the theory show us? So that's the theory. Eta equal to 1 corresponds to no losses. Eta equal to 0 corresponds to complete loss. And here you have 3 possible states. These are just the coherent states. That's the standard quantum limit. Here we have the known states in red, and here is the blue state, which is this state which has a 1-1 component. Now, you see that in the absence of losses, the known state as well as this psi state give results for the uncertainty in phase, which are much better than the standard quantum limit. On the other hand, as soon as losses increase, you see that the known state very soon becomes useless. In fact, the uncertainty in phase coming from the known state is larger than the one coming from the standard quantum limit. And this psi state remains always below the uncertainty given by the known state and also the standard quantum limit. Okay, so that's the theory. Now the experiment is like this. You see here again the uncertainty in the phase for several values of the transmissivity. Remember, the larger the transmissivity, the fewer are the losses. So again, blue is the state psi, red is the known state, and black here is the standard, is a coherent state. So you see that for eta equal to 0.2, that means high losses. The known state is much worse than this blue state, which is, however, very close to the standard limit. As losses decrease, you get this blue state below the short noise limit, and but the known state is always above it. So this shows that we have to rethink the best strategy if you have losses. And that's what we're going to do now. This, of course, is a numerical calculation. They have considered just 2 photons in this, of course, in this experiment. Now, important question, what happens when n increases? What can we say? Yes?
Did I understand correctly? So in order to apply this scheme, you have to know when a loss occurs, because you have to adapt your...
That's true. Their experiment was like that. So it was a demonstration experiment. Of course, it's not practical. But it's a demonstration because they looked for the best phase to measure the state. And they had to know when the loss occurred. Yeah. Okay. Now, we would like to develop a formalism that would help us to answer this question: what happens when n increases? Now, if we want to do parameter estimation with losses, then the general formalism actually looks very much like the one I showed you before. Again, we have a Kramer-Rao relation. It's a quantum Kramer-Rao relation, which bounds the uncertainty in the parameter below by this expression here, where the quantum Fisher information comes in. But now the quantum Fisher information depends on a density matrix, okay, because you have losses. And again, the quantum Fisher information is defined by the maximum of the Fisher information over all possible measurements. It is again given by this expression here of if you have a continuous set of measurement, you replace this sum by an integral. And this probability now, it's written like that. Before, it was just the average of these measurement operators in pure states, with respect to pure states. Now this average is replaced by a trace of the density operator of the probe times this measurement operator. This is the density operator after the probe has gone through the system, so it's dependent on the parameter. Now, one can show, and I'm not going to show this here, I mean, this is shown in these references here, but I'm not going to apply this. I'm going to use another method which yields analytical solutions. It can be shown that a general expression for the quantum Fisher information is this one, where this operator here is called symmetric logarithmic derivative, and it is defined by this equation here. Okay? So this defines the operator L. Now, just to make sure that this gives us the correct result for pure states, you see rho square is equal to rho, because rho is a projector onto a pure state. And therefore, the derivative with respect to rho, of rho with respect to x is given by this expression here. And now that's the derivative of a square, so we can write it like that. And by comparing this expression with this one, you see immediately that the symmetric logarithmic derivative in this case is equal to 2 times the derivative of the density matrix with respect to x. Now, we know that the density matrix dependent on the parameter is given by the initial density matrix of the probe sandwiched between 2 evolution operators. So if you differentiate now that with respect to x, you see that the generator will show up. And in fact, we get here the variance of the generator, okay? Which is the expression we had before for pure states. Okay? So this is the generalization. Now, of course, in the general case, we want to know what L is. And there is an expression for it that can be derived. It is given by this expression here. These are the matrix elements of this operator L, where Pi and Pj here are eigenvalues of the density matrix that depends on x. So you see that calculating this operator here implies really diagonalizing the density matrix, which, if the dimensionality of the system is low, you can do it. On the other hand, if you have a huge number of photons or a huge number of spins, that's very difficult to do. In fact, in the general case, not only L is difficult to evaluate, but there is no analytic expression for it. So that's the problem. And that was our motivation to propose a general method, actually, which I'm going to explain to you now, for estimating this ultimate precision limit in noisy quantum-enhanced metrology. Now, if you want to look at a very peculiar comment on this paper, you read that. It appeared in the same issue of Nature Physics, Beauty and the Noisy Beast. Well, okay, so anyway, so and that explains in words what has been done here. So before I go into the method, let me remind you of some results concerning open systems. Now, the evolution of an open system can be described by a Hamiltonian like that. So this is the Hamiltonian of the system. This is the identity for the environment. You have to add to that the Hamiltonian of the environment, multiplied, that's a tensor product, by the identity for the system. Oops, that's S here. And then there is the interaction between the system and the environment here. Now, so the idea then is that we are interested in the effective time evolution of the system S, and that is given by this reduced density matrix, which is obtained by calculating the overall state of the system and finding the trace with respect to the environment. So this gives me a map that takes the initial density matrix of the system onto the final density matrix of the system. So if we assume that initially the system and the environment are not correlated, that is, the initial state of the whole thing is given by the product of these two initial states, and we take the initial state of the environment as being the state 0, then the evolution of the total state is given by this expression, again, a sandwich of the initial state between 2 evolution operators. And now, if we want to get the density matrix of the system, we have to trace that over the environment. And tracing over the environment means calculating this expression here, where these states here form a basis in the Hilbert space of the environment. Okay, that's just the trace over the environment. And you see that if you look at this expression here, you see that it has this form here. So this part here is actually an operator that acts on the system, because this is the evolution operator of system plus environment, and I'm taking a matrix element here with respect to states of the environment. And here is another system operator. So you can write the outgoing density matrix of the probe, say, as that, and that's again what I called before this transformation applied on the incoming state. Okay? So you see that that's a quite general representation of the evolution of a density matrix. These operators here are called Krauss operators, and this is the Krauss decomposition of the evolution. This transformation here we call a quantum channel, and the differential form of this evolution leads to the master equation for the reduced density matrix of the system. So this is a kind of integral form of the master equation. Now, let me give an example of that, and this example I'm going to come back to it in the fourth lecture of the course. So this is the amplitude damping channel. Now, you see we have here a state of the system and a state of the environment, and this evolves because of this unitary evolution here. And this evolution is such that if the system is in the zero state and the environment is in the zero state, they remain so. If you want to give a physical meaning to that, just think of the states of the system as the ground state and the excited state of a two-level atom. And the states of the environment you can think as the vacuum state and the state with one photon in the environment. Okay? So in this sense, this set of equations here really correspond to the so-called Weisskopf-Wigner approximation that calculated the state of the decay of an atom if we set this parameter p equal to 1 minus exponential of minus gamma t. So you see, if you look at the second equation here, p is thus the transition probability from this initial state to the final one. So it tells you that you have some probability of remaining in the initial state and some transition probability that is such that the atom goes to the ground state and releases one photon into the environment. Okay? Now, so this would be the decay of an atom with zero temperature. Of course, the reduced density matrix that you get by tracing out the environment degrees of freedom coincides with the solution within the Markovian approximation of the master equation corresponding to the Hamiltonian of a two-level atom interact with a continuum of electromagnetic field modes. Okay, so you get the same final solution. Now, writing this equation in this way has also an advantage. Instead of just replacing immediately p by its time-dependent expression. And the advantage is that this map here can actually represent another process. If you set p equal to sine square of omega t over 2, this will describe Rabi oscillations between the atom and one mode of the electromagnetic field. So we can treat both problems using the same set of equations. Now you see that here we are interested in the atom, but still you write the evolution as a unitary evolution of atom plus environment. Now, from the definition we had before of Krauss operators, we can immediately calculate them from this equation, just using this definition. And then we get this set of operators here, just two operators. And that means that the evolution of the reduced density matrix can be written like that. That's the Krauss decomposition. So by using these matrices here, I get this expression, which is very suggestive. In fact, if you set p equal to 1 minus exponential of minus gamma t, you see that the excited state probability decays, because 1 minus p is e to the minus gamma t, decays exponentially. With rate gamma, and by decay it populates the ground state. Okay? That's an added term here. While the coherences decay also, but with rate gamma over 2 because of the square root here. Okay? So these are known results in atomic physics. Now, what we are really interested is in the purification of an evolution. What is that? So given a Krauss decomposition of a channel, like the one I showed you, it is always possible to find a unitary evolution of a system, of the system we are interested in, plus an environment. That is, if we pick up a basis, say this one, in the system of the system S, and as many orthonormal vectors in an environment as the number of Krauss operators, we define this unitary evolution in this way. Okay? So this is the Krauss operators that come in the evolution of the reduced density matrix for system S. Now we attach to each state a state of the environment with sum over I, and we define this evolution by that. It's easy to show that this equation here leads to norm conservation. And if norm is conserved, that means that this transformation here can be extended to a unitary operator acting on the whole space. Here it acts only on the 0E, but you can show that this can be extended to the whole space. So just this is shown in books on quantum information. Just take it as a theorem. It is a result that we get there. So you see, that could be very helpful, because if we cannot know an analytic expression for the quantum Fisher information for open systems, if we can extend the system and transform the reduced evolution into a unitary evolution, then we are great, right? Because for the unitary evolution, we know what is the quantum Fisher information. Okay? So that's the main idea. Of course, this unitary evolution here is not necessarily the same as the one that we had before. When we derived, say, for instance, the reduced evolution of the density operator. That's not needed. In fact, these vectors here, they may span an effective environment with smaller dimensions than the real environment E, which leads, however, to the same dynamics for all states S. Okay? So, you know, this E prime here, that's important to understand, is not a physical environment necessarily. It's a mathematical environment that allows us to transform the open system dynamics into a unitary one. Now, so we are going to use this purification strategy in order to develop a general framework for estimation of parameters in noisy quantum-enhanced metrology. So the main idea is in these two journals. I do recommend the Brazilian Journal of Physics, first for two reasons. First, if you consult it, it will perhaps increase its impact factor. Second, because this paper there is much more detailed than the paper published in Nature Physics. Okay, so it's more pedagogical, so I really recommend it to students, for instance. Now, of course, this marketing that I did, that was a special order from the editor of Brazilian Journal of Physics.
Is there free access?
Huh? Yes, it is. Yes. Yes. So, given some initial state and some non-unitary evolution, we define in some extended space S plus E this evolution here. So, of course, the condition is that you cannot have any U here. You must have some U that gives you the reduced dynamics, the correct reduced dynamics. So we have that. Now, then we can see, we are going to see now that the quantum Fisher information for the system is always bounded above by the quantum information of S plus E. Okay? Now, we have shown that in that paper, but even with words we can show that. Because you see, the quantum Fisher information for the system amounts to finding the maximum of the Fisher information over all possible measurements made on the system. Now, the quantum Fisher information for the whole thing is the maximum of the Fisher information over all possible measurements made on the whole thing. So we have more freedom. More measurements are allowed, which means that this may be actually larger than this one. So you have this inequality here. The physical meaning of this bound is just the one I mentioned. So information about, this is the information about the parameter when S plus E is monitored. In general, you should get more information than if you probe this system alone, or at least the same information. Of course, we are interested in the least upper bound because we want to get as close as possible to this quantum Fisher information of the system. So somehow we should find a way to minimize this bound over all possible extensions of the system, okay, so as to get the best upper bound. That looks like a desperating problem, right? It looks difficult. Now, we have shown in this paper that this bound is actually attainable. In other words, there is always a purification such that this is equal to that. I'm not going to show you this derivation here. It's quite technical. It's based on a result obtained by Ullmann a long time ago. Okay, it's a theorem, and it's shown actually in the supplementary material of this paper. Now, so that's good news. Okay, so that means that eventually you could find some extension that gives us the quantum Fisher information of this open system. Now, the physical meaning of this is that, if you find this extension, then monitoring S plus E yields the same information as if you monitored S alone. You don't get any additional information, and therefore the two expressions coincide. Okay, so that's the meaning. Okay, so how do we solve this problem here? Well, there is a systematic procedure. It's not easy to implement. It doesn't work in all cases, which means that very frequently we have to use physical intuition to find this extension. Okay? But this systematic procedure was discussed in this paper here, and it's based also on a general result of quantum mechanics, which tells us the following, that if you have some purification of the evolution of some system, given by this expression, then any other purification can be written like this, where this operator is a unitary evolution of the environment alone. In other words, given two different purifications, they are always related by some unitary evolution applied on the environment alone. Okay, it's not a trivial result, but anyway, it's not difficult to show actually. Okay, you can read at the book, typical books of quantum information. It's shown there. Okay, so we define now the generator of this transformation by this expression, and therefore our job now is to minimize this quantum Fisher information for the whole thing over all Hermitian operators H, E, that act on E. And in this paper, we actually propose an iterative procedure for doing this. I'm not going to comment it here because I'm going to really use physical insights to get these expansions, to get these extended spaces. Okay, so let me give you now the first example, which is a pedagogical one. And the first example corresponds to a harmonic oscillator. There is some force applied to it, and we want to estimate the amplitude of the force. So that's the idea. Okay? Now, I use here renormalized quantities. This is the renormalized energy, so they don't have any dimensions, these quantities here. So X is given in the usual way in terms of the annihilation and creation operators for a harmonic oscillator. That's the momentum. And this F here is a dimensionless force that is expressed in terms of the physical force by this expression here. Okay, so we just work with dimensionless variables. Now, we go now to the interaction picture. In the interaction picture, the Hamiltonian is given by this expression here. You see A and A dag acquire these exponentials here. They evolve with time. And now we do the rotating wave approximation. That is, we write the cosine as a sum of two exponentials, and we neglect fast oscillating terms. So we get this expression here, which is very nice for our pedagogical purposes because it does not depend explicitly on time. Okay? So that's the interaction Hamiltonian. Now the unitary evolution is in the interaction picture is just given by this expression here. It's just the exponential of hi with it minus it. So it's given by this. And if you look at this expression, you see the exponent is proportional to the position operator. So in fact, this is a momentum displacement operator. And the displacement P is given by whatever multiplies x, except for the I, it's given by that. Okay? So that's just a momentum displacement operator. Now you see that the displacement of momentum depends on F. And that means that if we get P, we get F. So that's a way of estimating F. We measure the displacement. But then, of course, the displacement cannot be measured in a completely certain way because you have a dispersion in momentum of the initial state. So the uncertainty in the displacement will be given actually by the dispersion in momentum of the initial state. Therefore, this gives us an uncertainty in the force, which can be expressed in terms of the uncertainty in momentum by this simple expression. Okay, very simple model. Now, so delta F is now the uncertainty in the estimation of F, which is of course proportional, as I mentioned, to the uncertainty in the estimation of the momentum displacement. Now, here again you have the unitary transformation that produces this displacement in momentum. Now we apply what we know about the quantum Fisher information for pure states. So it's given by this expression here. It's proportional to the variance of whatever multiplies F. So it's given by this, which means that delta, the uncertainty in F, which is related to the uncertainty in momentum, is bounded below by just the square root of this expression, which is that. And E here, remember, is the number of repetitions of the experiment. So this is the expression then for the uncertainty force. Now, the standard quantum limit would correspond to delta, to the variance of x not equal to 1/2. That's a coherent state. And if you replace it here, you get this expression. Okay? So that's the standard quantum limit. The uncertainty or the variance of x naught, and therefore the uncertainty in the estimation of the force, does not depend on the energy of the harmonic oscillator. Okay? Now, if we want to get the ultimate precision limit in this case, we should maximize this variance under two conditions. First, we want the state to be normalized. Second, we want the average energy to have some value. So for us, here the energy, the average energy, is a resource. And we want to fix this resource. Okay? So just watch out, because this is quite different from the phase evaluation, where, remember, the standard quantum limit had a dependence with 1 over square root of n, the number of photons, which is related to the energy. Here, since it's a displacement, the standard quantum limit does not depend on energy. Now, so we want to maximize the variance with these two conditions. That can be done, for instance, using Lagrange multipliers. And if you do that, you find that there is a unique state that maximizes this variance, subject to this condition, and that state is a squeeze state. Okay? Furthermore, we can calculate this variance. It's given by this expression, which means that now this uncertainty in the estimation of the force is bounded below by this expression. And if E goes to infinity, that goes like 1 over square root of E. And I may abuse the definition of the Heisenberg limit by saying that this corresponds to the Heisenberg limit in this case. Okay, it's a dependence with 1 over square root of E. Now, you might find weird that there is this minus sign here. Maybe that gives us an imaginary value for the square root. No, because the minimum energy is equal to 1/2. That's the energy of the ground state of the harmonic oscillator. Okay? Now, watch out. We should also note that this uncertainty here is reduced, or this bound is reduced as the time increases. So measuring for a long time is better than measuring for a short time. This is typical of a noiseless system. This will not longer be true when noise is present, as we're going to see. Okay, so let's now consider the system with noise. And of course, in our paper, we have done master equations and so forth, but also this. And I find this much simpler in order to visualize the physics of the problem. So we now consider the noisy forced oscillator, and we deal with it by using a Langevin equation. So this is the time variation of the time variation of the momentum. That's the PDT. which is given by this force here. That's the source for the variation of the momentum. Then we have this damping term here. And then, of course, we should have a fluctuation force. That's the fluctuation dissipation theorem. And this fluctuation force we take with this correlation function, which means that we are considering here a zero temperature environment. Now, in the paper I mentioned before, we generalize this treatment also for temperatures different from zero. So we have an analytic result for the whole thing, okay? But here I just want to consider this simpler case. Now, you see that this is a linear equation, which makes life simpler for finding the solutions. So you can actually solve this linear differential equation exactly, and the result is this one. So the momentum operator time t is given by the momentum operator time 0 multiplied by this exponential, time plus a contribution from the force, plus a contribution from this fluctuation force here. Now, you see that this is really the momentum displacement. And I have defined here these quantities here just to make life easier for me, actually, so that I don't have to write all the time the explicit expression of d in terms of e to the minus gamma t and so forth. Okay? So, this is the momentum displacement. Now, the uncertainty in the momentum displacement is equal to the standard deviation of P of t of this operator in the initial state, because you see this is a Heisenberg operator. So we should take the standard deviation in the initial state. So we can write down that delta P is equal to the standard deviation of P of t, which is given by this expression here. Also, from this expression here, you see immediately that the uncertainty in the force is given by the uncertainty in the momentum divided by this factor, so it's given by that. And therefore, the uncertainty in the force is also given by the standard deviation in the momentum calculated in the initial state. Another important result that we get from this equation is that the variance of the momentum at time t is equal to eta times the variance of the momentum at time 0 plus this term here, where eta, remember, is given by e to the minus 2 gamma t. Okay? So this you get directly from this equation here. Okay, so if we replace that expression for the variance of momentum here, then we get that the uncertainty, the force, or the minimum uncertainty, if you want, is defined by this expression here. Now it can be expressed in terms of this, the sum of these two terms. And of course, because of the uncertainty relation, I can replace the variance in the momentum by 1 over the variance of x. And this should be therefore larger or equal than this quantity here. So we use the Heisenberg uncertainty relation. Now, clearly, the minimum uncertainty is reached for a minimum uncertainty state, because then this inequality becomes an equality. So if we consider this state, then we get this expression for the minimum uncertainty. And remember that this bound was obtained through a measurement of the momentum displacement. Now, we have not finished yet, because you see that this minimum uncertainty depends on the variance of x in the initial state. So we can still maximize this variance with the condition that the average energy is fixed. But we have done that already for the noiseless case. So we get that the best we can do is this. And then we get this expression for the minimum uncertainty in the estimation of the force. It depends on the energy. I leave to you to verify that when gamma goes to 0, this goes to the expression we had before, the noiseless case. Now, there is another way of getting the same result, which is using the Fisher information. Here I have used a sort of hand waving with uncertainty in the momentum and so forth. Now, we can do the following. We take the initial state as a minimum uncertainty Gaussian state. And if we do that, then the final state is also Gaussian, because the only operation we have a harmonic oscillator evolution, and we have displacement. But the displacement is a Gaussian operation. So the final state is Gaussian. So if you measure the momentum, then the Fisher information, according to the definitions I gave you before, should be given by this expression. You see, that's the probability of finding a momentum p in the final state of the probe. So that's the expression for the Fisher information. And in fact, you don't even have to calculate that. Because you see, since it's a Gaussian, we know that the quantum Fisher information is inversely proportional to the width of the Gaussian. We have shown that in the first lecture. So we can immediately write that. And then we find that the quantum Fisher information calculated for a Gaussian, that's the quantum Fisher information. There is no Q here. The Fisher information for a Gaussian is given by this expression here, where eta is given by that and d is given by that. You see, I almost made a mistake. I was saying quantum Fisher information, but it's not, because we have a specific measurement here, which is a momentum measurement. I have not maximized this information over all possible measurements. Okay? So now it's easy to check that if we have this Fisher information here, then the minimum uncertainty in the estimation of force is given by 1 over square root of this Fisher information, and this coincides precisely with the expression obtained before. Okay? So that the argument that delta p was given by the variance of p, which is quite intuitive, is confirmed by the Fisher information calculation. Now, important question, is this the maximum possible value? Maybe we can do better than that. So what we would like to do now is to find a bound for the quantum Fisher information for this open system, the damped harmonic oscillator. And in order to do that, we are going to use a physical picture, which will help us a lot to find this quantum Fisher information for the whole thing, and also for the damped system. First, we remark that the expression I wrote before, remember, that came from the solution of the Langevin equation. This expression here can be written in this way, where now this variance that has shown up here is just equal to 1/2, and that's the variance of the initial value of the momentum in the ground state of the harmonic oscillator. Okay? Now, this, I'm going to use a sentence by Asher Perez, which I find very nice. It is well known by the people who know it, that this relation between the variances is typical of a beam splitter. Okay? In other words, if you have a beam splitter here with some incoming field, and then we have vacuum coming here, you have this outgoing field here. Here, you have these transmitted vacuums and also the reflection from this incoming field. If you have this configuration, then the variance of this quadrature, of the corresponding quadrature of the field, of the outgoing field, is given precisely by this expression. Okay? So it says that it has some contribution from the transmitted variance, if you want, of the incoming field, plus another contribution from the reflected variance of the vacuum. That's a loosey way to speak, but that's the idea. Okay. So then, this motivates us for the following idea. We can, as we saw in the experiment by Walmsley, we can mimic the effects of noise with a beam splitter. So we do that. We have the incoming state of the probe now, and now, of course, we replace the oscillator by a field mode, and the environment for us will be another field mode that takes photons out of the incoming state. Now, so these are the losses. Of course, they depend on time, but I can consider that this is just the transmissivity of this beam splitter. Now, this will be a purification of the system. Now, of course, for the system, I already have here the effect of losses. Some photons are taken out, but I still don't have the effect of the force. So I do that with a formal trick. I consider another beam splitter here with a transmittivity that goes to 0 and some incoming field with an intensity that goes to infinity in such a way that this product remains finite. Okay? So this will give me a displacement of some quadrature of the field by this amount, which is the displacement I had in the Langevin equation. You see, I'm mimicking that process with this kind of setup. Now, if I look at this path here, that corresponds to the harmonic oscillator I had before. I have decay, and I have a displacement of momentum. Now, the environment is still there, and in fact, if I want to measure, remember, the quantum Fisher information corresponds to global measurements made on system plus environment. So I add a beam splitter here and another beam splitter here, so that with this beam splitter I can get these global measurements, which may imply interference between the two modes. Now, if we do that just like this, I don't get a good result. I get that the quantum Fisher information for the whole thing coincides the fact with the quantum Fisher information for the noiseless system. It's not interesting. So what I need to do is to erase some possible information on the joint measurement, possible information on the force. I have to erase that. Because remember, if I erase this information on the additional information on P, that joint measurements can give with respect to measurements made only on S, if I erase that, then the quantum Fisher information for the whole thing will coincide with the quantum Fisher information for the system, because I don't have any additional information coming from the joint measurement. Okay? So in order to do that, I do a unitary transformation on the environment. Remember, any two purifications are related by unitary transformation of the environment, and indeed, this unitary transformation does not change the reduced description because it's applied on the environment alone. And then I do the same trick here. I inject, formally, a coherent state here. I take the transmissivity of this beam splitter going to 0, alpha 1 going to infinity, so that this remains finite. And this produces a displacement in this mode, which I write like that. F is the force I want to estimate, and G is a function to be determined. And now you see, I have a closed system, I have a unitary system here. So if I have a unitary system, that means that I can calculate the quantum Fisher information for the whole thing. Now I have this function here, which I can adjust. And in fact, we have done just that. You calculate the quantum Fisher information for the whole thing. And you choose G to minimize this quantum Fisher information so that you get the least upper bound for the quantum Fisher information of the system S. Okay? So if you do that, you find this expression for the quantum Fisher information of the whole thing. Maybe you remember that. In fact, that coincides with the expression we had before when you solved, say, the master equation for the system alone. Okay? So, furthermore, this expression here depends on the initial state only through this variance. So it is valid for any kind of initial state. And it's the best we can do if we measure the whole thing. So since it coincides with the expression before, you see the expression we had before, in principle, was smaller than the quantum Fisher information for the system, but now this is an upper bound for the Fisher information, for the quantum Fisher information of the system, so the two have touched. We have saturated this upper bound. So we can say now that minimum uncertainty Gaussian states and momentum measurements are the best choice in this case. They saturate the bound. Furthermore, we have now an explicit analytic expression for the quantum Fisher information for estimating a force that applies to a damped harmonic oscillator. There it is. So that's the expression. Now in terms of E, we have, of course, maximized the variance of X in the usual way for fixed average energy. So we have this expression here. Just to remind you, this is the physical force in terms of this dimensionless force. And we have done here minimization of the bound, which implies maximization of the variance in position. Again, we get a squeezed state. And now you see that depending on which term dominates, one gets the standard or the Heisenberg limit. If this term dominates, that gives me a result that is independent of energy, which is the standard limit. If the other term dominates, one gets the Heisenberg limit. In fact, these are the two conditions. This leads to standard scaling. That means energy high enough. This leads to the Heisenberg scaling. And that also shows that for sufficiently large energy, we always go to the standard scaling. Okay? No matter how small is the loss. Now we have extended this result to a thermal reservoir. You just have to do this replacement here. Now you see that if you look at this expression, you see that this bound saturates as time grows, because when time grows, eta goes to 0. So this term goes out. Here you just get the 2. And then you get this expression here. You expand eta in terms of I mean, this is eta, gamma t is going to infinity, so eta is equal to 0. And you just get some expression that does not depend on t, which is given by this. So I have here replaced 1 minus eta by this expression here, which involves the thermal photons in the reservoir. So this saturation means that it does not pay to wait for a long time, as in the noiseless case. After some time, you just get the same bound. So there is a way to do better than that, and that's using the strategy of dividing to conquer. You see, suppose the force acts during some total time given by t total. We probe the force not during this total time, but during some time tau. We measure the system, which is smaller than that. We measure the probe system. We reset the system and repeat this procedure n times, with n given by this, total time divided by tau. Now, you get some expression. I'm not going to show it to you. It's complicated. You minimize the measure uncertainty with respect to tau. So you find the best measuring time. The fact that there should be a best measuring time is also intuitive, because if you measure for a very short time, you don't get information on the force. If you measure for a very long time, you saturate the bound. So there is some intermediate value, and we can find that. And if we find that, let me show a result in a simple case. We consider this diffusive limit, which is a double limit. We take gamma, the damping constant, going to 0, the thermal photon number going to infinity, with this equal to d, a fixed number, which happens to be the diffusion coefficient. Just believe me now that this will give you the diffusive equation. Okay? So now, with these conditions, we can compare our results with the results obtained in Weinland's group, published here. So they got this for the minimum uncertainty in the estimation of a force. It depends on the diffusion coefficient. And you see that when the diffusion coefficient goes to 0, this lower bound goes to 0. Which we know cannot be true, because we should get then the noiseless case, which does not give 0 as a lower bound. So our result is this one. We get this correction here. And you see that when d goes to 0 now, this cancels with that, and we get precisely the noiseless case solution. Okay? So this shows a little bit the force of this method, of course, in this special example. Now, further generalizations of this, in our paper, we treated the problem with estimation of the amplitude of some force, which has some time dependence. And you know the time dependence. You define this amplitude here in such a way. You say that the maximum of this function here is equal to 1. And we have considered the estimation also in this general case, which means that we can treat the broadband case and the narrow band case, and that you can see there. Now, an interesting treatment for waveform estimation was published here by Tsang, Weisman, and Caves. And they have a general formalism. They exemplified it by applying to this Hamiltonian here, which you know already. And they assume that this force f of t is a stationary process. That means this correlation function depends only on tau equal to t prime minus t. And then they show that in this case, the quantum Kramer-Rao bound becomes a spectral uncertainty principle, which is this one. These functions here are defined in this way. They are just This is the spectrum corresponding to this noise process x of t. So this is the spectrum corresponding to delta q, the standard deviation of q. You calculate in terms of the correlation function. And this is spectrum corresponding to the force, standard deviation of the force. And this is the power spectral density of decimation error. So this is a generalization for when you have some waveform that you don't know in advance what it is, say. Okay? Now, so this is one of the examples. Let me give you another example, which is quantum limits for lossy optical interferometry. We do the same trick here. We have some lossy interferometer. We consider that we have a beam splitter here, so it reflects part of the photons. And one uses a similar strategy as before. We want to do a phase displacement on the environment so as to remove additional information on the phase theta. So that's the idea. And if we do that, just using the same procedure that we used before, we get the following. So you now calculate the quantum efficient information for the whole scene, including this mode of the environment that is a reservoir for the system. And we minimize it with respect to this parameter theta prime. By doing that, we get an upper bound for the efficient information of the system, which is given by that. And it depends on the average number of photons in the initial state and on the variance of the number of photons in the initial state. And now again, you can look at two limits here. That depends on the relative weight of these two terms in the denominator. If noise, in the noiseless case, that is eta is very close to 1, you have this much smaller than this one. And you see that then you can neglect this term in the denominator with respect to this one. This cancels out this one, and you just get the quantum efficient information for the noiseless case. On the other hand, in the opposite limit, when you have heavy losses, eta is much smaller than 1. It is this term that should be neglected. And then the variance cancels out, and you get a standard limit kind of scaling. Okay? And this can be done, can be seen with more clearly by dealing with states with well-defined photon number, like this one. Then using this procedure, we get this uncertainty for the phase. And again, this shows that first, if you have n sufficiently large, you always get a 1 over square root behavior, because this n here dominates of all the terms in the numerator, and you have a square root here. In fact, the two conditions are this. If n is small enough, as compared to this expression that depends on the noise, you get the Heisenberg scaling. If n is large enough, you get the standard scaling. And again, this shows that no matter how small the noise is, if n is large enough, you always go to the Heisenberg scaling. Now, important question, how good is this bound? In this case, it's not exact. We just got an upper bound for the quantum efficient information for the system, but it turns out to be very good. So this plot is the square root of the quantum efficient information calculated numerically. How do you do that? You have to normalize, you have to diagonalize the density matrix, you have to use that singular derivative operator and logarithmic, and that's how you do it. And this compares the quantum efficient information with our bound. Of course, our bound is always larger than the quantum efficient information, so this is smaller than 1, for several values of n, n equal to 10, n equal to 20, 30, 40. You see that these things here approach as n goes, as n increases, this limit here, 0.8. And now we have plotted this minimum here, the minimum of this curve, as a function of n. And you see that indeed goes to this value 0.8, which means that we are not too far from the quantum efficient information. Now you may ask, why are you plotting square root and not the ratio between them? Because I'm interested in the uncertainty. And the uncertainty is inversely proportional to the square root of the quantum efficient information. Okay? So this will give me an uncertainty which is 20% wrong, say, with respect to the one given by the quantum efficient information. And finally, final example is phase diffusion, which again is an instructive example. We don't have an exact solution, but we can find some interesting bounds. We consider phase diffusion in an optical interferometer. Now this can be described by this master equation here, where now this operator is just the number operator. Or if you don't feel at ease with this master equation, maybe you'll feel at ease with the solution. The solution of the master equation is given by this expression. And you see beta here is equal to gamma t. And you see from this expression that the coherences decay. If n is different from m, you have a decay here. On the other hand, if the populations do not decay, if n equal to m, this does not decay, which is typical of a dephasing process. Okay? So that's the solution. And what we would like to do is to use our method to extend the space so that we can treat this system with a unitary evolution. And the trick is the following. We have here the optical interferometer contribution. That's the sensitivity to phase. And we add this term. This term displaces the state of this mirror here. You can consider this as a mirror of the interferometer. You can treat it as a harmonic oscillator. And this displaces the mirror depending on the number of photons in the cavity. This is actual radiation pressure term, okay, which displaces the mirror depending on the intensity. So you add this term, and that's a way to accommodate an environment that is coupled to the number of photons. So if we trace out the mirror, you get the same master equation we got before with losses. On the other hand, if we calculate this upper bound for the quantum Fisher information using this kind of extended space, we get just the free, the lossless case, which means that this is still not good. That's not a good extension. In other words, if we do joint measurements on system plus environment, with this kind of extension, we do get additional information on the diffusion than by measuring the system alone. So we would like to get a tighter bound that should depend on the diffusion constant. Now, I showed you before that we can get that by using this transformation in the environment. And what we are going to do is to apply this transformation, which now depends on the momentum. We already have the position here. We apply this transformation on the whole system and calculate lambda so as to minimize this upper bound of the quantum Fisher information. Now, you may ask, how did you dream of that? Why that? In fact, in the paper I showed you before, we have a systematic procedure for getting these extensions. It's not always very simple to do it, but in this case, it gave us the hint that we should do this. Okay? That's a first order approximation, if you want. Now, so we get now this. So we have to minimize it with respect to lambda. And if we do that, we get this nice expression for the uncertainty in the phase. You see that this is typical, actually, of uncertainties due to independent noise sources, right? You have to add these uncertainties in this way. And this is the intrinsic quantum feature. It depends on the variance of the number of photons. This is the phase diffusion contribution. And that's the optimal value of lambda. Now, an important property of this bound is the presence of this constant term here. That means that the presence of phase diffusion is, in general, more important or more detrimental to phase shift estimation than the presence of photon losses. Because for photon losses, we showed that for n sufficiently large, uncertainty goes to 0. Because the dependence is with either 1 over square root of n or with something intermediate between square root of n and n. So this is bad. So that's the result we get. And we claim that this should be an upper bound. That should be a lower bound for the uncertainty. Corresponds to an upper bound for the quantum Fisher information, but should be a lower bound for the uncertainty. Now, so let's compare this result with numerical calculations done for Gaussian states by these people. you see, since they used numerical calculations, you see that their number of photons go up to this. Because the numerical calculations are tough. You have to diagonalize numerically a density matrix for the system. So this is the dots here correspond to the results by Mateu Paris and the other collaborators, these people here, Genoni, Olivares, and Paris. This is a close-up of this region here. You see that these three lines here correspond to different values of the diffusion constant, which depends on time, of course. So from bottom to top, beta square actually decreases. So this is higher beta, lower beta, and the lowest value for beta square. And you see that this comparison shows that so this is our bound for the quantum Fisher formation. So this shows that we are always above the numerical values, as we should, because that's an upper bound for the quantum Fisher formation. That also shows that we are not so far. That, okay, it's not the exact solution, but we are close actually to the numerical results, and we can actually extend this and to other regions. And we do have here a lower bound for the uncertainty that can be compared, say, with experimental results. Okay? So in order to do this plots, we had to do a trick because he was using Gaussian states. And for Gaussian states, we have this inequality here. So we replaced this by this expression, which means that we got worse results than we could have because we're still doing some majorization here. So that's it, folks. In the fourth lecture, I'm going to show how quantum metrology can be applied to the problem of energy-time uncertainty. And I'm going also to show you that our quantum Fisher information here will replace the variance in the energy when you consider open systems. And why is this interesting? For several reasons. First is that we would like to have a unified treatment for closed and open systems. In the past, people have treated them in a separate way. Okay? So for closed systems, you have this delta E, delta T. For decaying systems, you should look at the line width, say, and find the delta E corresponding to that. Yeah? And here you have a unified treatment that can be applied to any system, closed or open. Furthermore, that is directly related to what one calls quantum speed limit. That is the evaluation of the maximum possible speed of transformation of a state, which means, for instance, that you have some spin and you want to flip it under some conditions, including noise. In principle, one can use these formulas to calculate what's the maximum speed you can get. So I think it's relevant for several problems, and we are going to discuss this in the last lecture. Thank you very much for your patience.